Hello, everybody in 21X. This is Jay. I'm one of your LAs. We got a little rushed at the end of our session since Dr. Rebecca wasn't there today. So I've decided to record this little video for you guys, and as some of you may remember, this is the problem from Wednesday's class, and I'll start covering it. I'll just reread the problem statement for you. So, a plastic block of mass m is launched across a frictionless surface with an initial velocity of v0. There's a patch of dirt on the ice, and you happen to know the coefficient of kinetic friction between plastic and dirt, UK, as anybody should know off the top of their head. And the width of the dirt patch is d. A few meters past the patch of dirt, you notice a hill of height h, right here. And the patch of dirt is right here. As the hill flattens out at the top, point E is at the same height, y equals h. There's a spring with constant k against a wall. So this spring right here has spring constant k. So let's see what questions are asked of us. If the block has initial speed v0, at which of the labeled points could the block possibly come to rest? So, come to rest. What we know from a kinematic standpoint is that comes to rest means v equals 0 or velocity equals 0. What places could that possibly happen at? So, let's go one by one, systematically analyze which ones can and which ones can't they stop at. Okay. A. So, if it has some kinetic energy, right, that is to say that it is moving, and it's moving rightwards, and it's frictionless. If there's no friction to slow it down before A, when it gets to A, it's going to be moving the same speed, and so it would not have stopped, and it cannot stop at A. So A is not going to be going on this list. Now let's look at B. So B, running up to it, there is friction. There's something to dissipate the energy carried by the block. So the kinetic energy the block has can be taken away from the friction and turned into heat. So B is a valid answer. So let's write down B as one of our answers so far. So B. Now let's look back right here and look at C. So C, if it comes out of this section of dirt and it has some initial, some velocity after the fact, then there's nothing slowing it down in this region. And once it gets to C, it's still going to have a velocity. And if it has a velocity, it's at least going to make it somewhere up this slope, which leads us to part D. And so if it has some energy and it comes up, it's going to make it partially up this slope at the very least if it comes off of B with some energy. So C is not in here, D is, B is, A is not so far. Right? So let's add D to this list. So D as well. Now, coming to the final 2 points, E. E is at this very top point. And you might say, oh, if it gets up the hill, then it's going to keep going. But there is this edge case where it has enough energy to get through this dirt section and exactly enough energy to get up this ramp. So there is the possibility that it has just enough energy to get up through the dirt and up the hill, but stops at the very, very top. It's not a stable place for it to stay, but it can get up there and it can stay there. All right, so E, let's add E to our list. And then finally F. F right here means that it's going to compress this spring. And if we're going to be compressing this spring, and it's going to stay there for a moment, so instantaneously, just for one moment, same way at D, it only comes to rest for a second in some cases. It can come up to F, stay there for just one solid moment, V equals 0, boom, it is stationary for a moment, and thus it comes to a rest. So F is also a valid answer. So we have our 4 points so far, B, D, E, and F. Let's see what the next question asks. Assuming the block has enough initial kinetic energy to come to rest at point F, What forms of work and energy should be included in our energy table or energy bar chart? Okay, so the obvious one here, at least it should be obvious now, is that it has kinetic energy. Like I said, kinetic energy implies that there is movement in the system, and there is movement at the very beginning. And if it makes it through B, and it still has more kinetic energy, but it has less, so it has less kinetic energy after it goes through this section of dirt. What happened to the energy? We know that energy is conserved through a system, and if the system is the ground and the block, this energy must have gone somewhere. So far, we know that we have to have kinetic energy, EK, and something that gets rid of that, so E thermal. Also known as negative work dissipated. And so if it gets to C, after all of this, which it needs to, as it comes up this ramp, we know we're going to turn kinetic energy into gravitational potential energy, right? So it gains gravitational potential energy as it goes up the slope, and as it gets to E, a lot more of it is in this potential energy. It's going to have mgh worth of energy at y equals h. We so far have E kinetic, E thermal, and the potential energy due to gravity. So springs have a potential energy associated with them. And by compressing this string, we add energy into the spring and storing that energy there. Okay, so let us also add U spring. So these are our 4 types so far. And those are what we're going to deal with for the rest of this problem. So those are what's going to go into the energy table and the energy bar chart. So let's go on. Construct an energy table. We should have seen this coming. And assuming the block makes it to the points B, D, E, and F and comes to rest. So initially this problem just said up to F, but because I'm adding this and creating this supplemental activity, I'm going to go through each one of these just for practice. And so hopefully if you didn't understand F, but you see me building up to getting to F, you'll understand it just a little bit better. Construct an energy table assuming the block makes it to the points B, D, E, and F and comes to rest. Determine the energy equations. Find symbolic expressions for the initial velocity that allows the block to reach each point. So that's a lot of words. It's hard to parse, but let's look at this piece by piece. So this energy table, what is it asking from us? So initially, what is the kinetic energy? What is the gravitational potential energy? What is the spring potential energy? And what is the energy that has been dissipated? So initially, you're at ground level. There's no gravitational potential energy. There's also no spring potential energy because you're not compressing the string at all. And you haven't gone through that rough patch of dirt. So the only thing that you have right now is your kinetic energy, which is 1/2 mv0 squared. Say we're stopping at V, then we should have 0 kinetic energy if we're stopping at B. And then our potential energy due to gravity is also still 0. Our spring is also 0 because we're not compressing the spring and we haven't gained height. And then our dissipated force should be, force dot displacement. And for this case, the force is friction. And our displacement would be some distance into B. We know that on a flat plane, friction is going to look like this. Mu K, mg, that's the force, and then times the distance, which is going to be delta x naught. And then if we look at our equation for that, this energy here should be equal to this energy here. So let's add everything up in that line, 1/2 mv0 squared, because everything else is just 0, and then equals mu k mg delta x naught. M's actually cancel here, so the mass doesn't actually matter. What we could actually calculate here, which we don't otherwise know, is delta x naught is going to be equal to this v0 squared over 2 mu k g. Now let's go to D and assume that we stop at D. So at D, we no longer have any kinetic energy. We're stopping there, so there's 0 kinetic energy. Now, our potential energy to do the gravity is now different. We're going to have some delta y. So we're going to have some mg delta y. And we're going to be able to calculate what delta y is based on this initial velocity. And we'll get to that in a second. Still, spring is not compressed, so 0. And the dissipative force, now delta x naught is not true anymore. Now it's the full distance d. So we're going to say mu k mg d. And then let's do the same thing we did last time. We have 1/2 mv0 squared on the left-hand side, and that's going to be equal to mg delta y plus mu k mg d. Yet again, masses cancel, and then what we can do here is we can solve for delta y, and we'll see that delta y, moving everything to one side and then dividing by g, is going to be 1/2 v0 squared minus mu k g d all over g. And this would be a valid expression for if you were asked what the height up the ramp would be. And now for E, E up here is going to be at the very top of this slope. So it just comes to a stop. So we know that 0 kinetic energy, and instead of delta y, we actually have mgh, 0, and still mu k mgd. Now, it's actually going to look very similar to this, but instead we might want to ask, well, we know what h is, we can measure that. Now we might ask, what was the velocity beforehand to make it just get to E, but no further and no sooner? So let's set up our equation again. 1/2 mv0 squared equals mgh plus mu k mgd. M's cancel, and we have that v0 squared is going to equal to 2gh plus mu k gd. Sorry, quick correction. I forgot to multiply the 2 over to both terms, which I should be better about by now, but I missed this 2 right here. When I multiplied by 2 on both sides, I only multiplied it to this and not to this as well. Remember, distribute to both terms. I implore you to go ahead and try F on your own. I know we did it in class, but it is good practice and you lose nothing by trying it right now before I do it on camera. All right, so F, if we're coming to a stop, again, boring, I know by this point, but 0 there. And our potential energy due to gravity is yet again mgh, is 1/2 k delta x1 squared. And then still the dissipated energy due to friction was going to be mu k mgd. There's 2 ways we can go about this. We can either ask, how much did the spring compress? What is the initial velocity? And what we're asked is what is the initial velocity. So let's set up this equation again. 1/2 m v naught squared is going to equal to mgh plus 1/2 k delta x 1 squared plus mu k mgd. In this case, you can't cancel out m, but we can divide m over anyway. By dividing by m and multiplying by 2 on both sides, we get v naught squared isolated, and that's going to equal to 2gh plus k over m delta x1 squared plus 2 mu k gd. And taking the square root of both sides, that would be your final answer. Let's look at the energy bar charts. So instead of looking at each one in every single case, right, let's just look at initially and finally. And by finally, I mean at point F. So we know initially there's actually no other kinds of energy other than kinetic. Kinetic is actually going to be the total energy. And at the end, there's actually no kinetic energy. Whereas there is some gravitational potential energy, maybe it's even a little bit higher. There is some spring, and there is some dissipated energy. And if you added those up on top of each other, you would see that they reach the exact same height. That's because energy overall is going to be conserved. So the final bar chart should look like that. I hope this was helpful. I put a little bit of work into this, and I hope it's useful in some way. Thank you guys for your time. I hope week 8 isn't going too stressfully. I know that term is coming to the end, but let's stick it out and have a good Friday class. All right, bye. Right. All right. Okay.